let's look at the entire rest of the semester. We've got an assignment due a week from today. That's the one that I just handed out. And then on Friday, the 3rd of May, you'll have homework 14 due. We won't have a week between assignments there because Friday, the 3rd of May is the last day of classes. Unfortunately, I'm not going to be here for the last day of classes. I'll be down in Clemson helping to write the FE exam, so we'll have an online class that day on the 3rd. So the way that you'll submit the assignment is just to cram it under my door. Just mash them all under there, and the cleaning guy usually sorts it out, puts it on my desk, and sometimes we'll grade a few problems. Final exam Tuesday the 7th of May, Friday the 10th of May for the other section. So, and then not pictured there because it's always a mystery whether we'll have a quiz on any given class period. We'll probably have a quiz on Wednesday. 48 hours from right now, you'll probably be taking a quiz. Any schedule questions?
So the exam is going to be like using the computer like last, like the midterm? Or
The final exam? Yes, it'll definitely include some questions where you need the computer to solve it. These water surface profile problems in particular are a lot easier to solve if you've got access to Excel. An odd noise. Must just be the fan of the projector. Other questions? Oh, it's the laptop? Okay.
Like a V8 engine or something.
It's because it's warming up. It's spring. Yeah. All right. When it bursts into flames, I'll know which direction to run.
Make sure you sit under a sprinkler.
Last time we did the numerical integration method, and actually in the in-class exercise that you saw, we applied the numerical integration method to something that's more normally solved using the direct step approach. Remember that in the in-class exercise you worked last time, you were actually, in the second part of the problem, finding the distance between two sections where you knew both of the depths. So in water surface profile problems, we always know the depth at one location, and we're trying to find either how far upstream is it to a certain depth, or at a certain distance upstream or downstream, what is the depth there? And so we are trying to integrate a curve or extrapolate the shape of the curve to find out what some new depth is. Now, in the direct step method, also known as the step-by-step method, what we'll do is break up a long curve up into multiple segments. In the in-class exercise, you were seeing that for that particular example, there didn't seem to be much difference between solving it in a single step versus breaking it up into two steps. And that's because it was a relatively short distance between the 2 points where you're trying to find the depth. But oftentimes, the curve is really long, and so we'll have to come up with some other way to find out how the depth is varying as we move up or downstream. And so what the direct step method does is it looks at specific energy at 2 points. And it compares the specific energy at the 2 points and also takes into account the difference between the slope of the channel bed and the slope of the energy grade line. And that's best illustrated by stepping through this diagram. And so between the two sections, where one is section upstream and two is the section downstream, we're going to be looking at the sum of all of these components that give us the energy. The total energy line starts off here at the top, and there's a horizontal dashed line that's parallel to horizontal datum. And what you'll notice at 1 is if we go up to the top there, it's the slope of the channel bed times dl, where dl is the distance between 2 points, the depth, and the velocity head. Now, specific energy is only the energy above the channel bottom. And so here, specific energy is going to be y1 plus the velocity head. Okay, and now at 2, we go up just having the depth, elevation head, and now the distance between the horizontal line and the total energy line is the slope of the energy grade line, S sub F, so that tells us what the slope of this energy grade line is, multiplied by dl. So that's how we find that distance there. Okay, so when we combine all three of those terms, the energy at 1 is equal to the energy at 2. Now, of course, the slope of the energy grade line and the slope of the channel bed are not going to be equal to each other. If they were, this would be uniform flow, and we wouldn't be trying to classify water surface profile. So we can expect that those are not going to be equal. If we rearrange things a little bit, if we move the specific energy to groups, so the specific energy being the energy above the channel bottom at 2, minus the energy above the channel bottom at 1, then that is the specific energy at 2 minus the specific energy at 1 is the difference in the slopes times dl. So we're just moving the specific energy portion of this total energy expression in groups, and then what's left over is the difference in the slopes times dl. Now remember that in the numerical integration method, we considered properties at the midpoint between 1 and 2. We were trying to find out what was the slope of the energy grade line at the midpoint, because the slope of the energy grade line at 1 is going to overpredict. The slope of the energy grade line at 2 is going to underpredict. So if we average the slope, then that gives us a little bit more of an accurate result because of the curvature of the energy grade line. And when we combine those two things together, the direct step method essentially says that the distance between 2 points where you've got a change in specific energy can be estimated by what is the change in the specific energy divided by the difference in the slopes, the difference between the channel slope and the energy grade line slope at the midpoint. And just a couple of guidelines when we apply this technique is that if we have subcritical conditions, we'll usually start downstream and work our way upstream. And the opposite is true for supercritical conditions. For supercritical conditions, like flow coming from under a gate, where we would generally start is the known depth upstream and then work our way downstream along the curve. We'll break up a reach into multiple segments, and we'll solve that in a single spreadsheet. I'll show you the different columns, and it's a little bit unusual because we'll have multiple rows for each step, whereas normally each step fits onto a single row. Because we're taking the average at different sections, we sort of have to do things a little bit differently. But to ensure that the method is relatively accurate, we try and make these steps as small as possible. The more steps you break this up into, the more accurate it's going to be. And the guideline is that you shouldn't allow the depth to vary more than ½ a meter in each step. And so a way to illustrate that problem is with an example. And we're going to work this example together very slowly so that everyone can get the columns on their Excel, have a nice example to work from as you're doing the homework. So there's some preliminary stuff, like when we're classifying a water surface profile, remember that we want to find the critical depth, the normal depth, and then with those two things we can find out the water surface profile type, meaning not only M versus S versus C, but also being able to classify whether it's profile 1, profile 2, profile 3. So we'll go through those preliminaries, and then we'll start setting up the method itself. Okay, in this problem we've got a rectangular channel. All right, a rectangular channel that's 7 meters wide and it's carrying 15 cubic meters per second. So critical depth, of course, is the flow per unit width squared divided by G to the 1/3 power. Okay, and if we have 15 cubic meters per second going through a 7-meter wide channel, then the flow per unit width, 15 cubic meters per second divided by 7 meters. So that's the flow per unit width. We'll square it, divided by G, 9.81 meters per second squared. All of that to the 1/3 power. It gives us a critical depth of 0.7764 meters. All right, normal depth. All right, we've got 15 cubic meters per second. The n value 0.020. The channel area is 7 times the normal depth to the 5/3 power. And then the wetted perimeter is 2 times the normal depth plus 7, which is the channel width, to the 2/3 power. And the slope 0.0015 to 1/2 power. All right, so we solve that either with the calculator or using Excel, and we find that the normal depth is 1.195 meters. Okay, so with the normal depth and the critical depth, what's the water surface profile type? On your paper there in the notes, why don't you go through the logic of classifying the water surface profile type? And it always helps to do a drawing for that. So I'd recommend doing a little sketch for yourself to classify the water surface profile. Jordan, do you know what kind of a water surface profile we've got? Based on the fact that normal depth is greater than, the actual depth of 3.8 meters right here at the obstruction. That's greater than the normal depth. And the normal depth is greater than the critical depth. So with this, what kind of water surface profile have we got?
M2.
It is an M. And how did you know it's M? You're correct that it's M. Lucky guess, or do you remember what the logic is for mild versus steep slope? Like how do you know if it's an M versus an S?
Your normal depth is above the critical depth.
Right. So y sub n greater than yc, that's how you know that it's a mild slope. And then whether it's 1, 2, or 3 depends on where is the actual depth y. And so Normal depth and critical depth, these two imaginary lines delineate three zones. Zone 1 is above, zone 2 is between, and zone 3 is below.
M1.
So it's an M1, yeah, because this flow depth of 3.8 is greater than the upper imaginary line, the normal depth. So this is an M1 profile. And characteristic of an M1 profile is that it's getting shallower upstream. So we've got some obstruction, and then in the upstream direction, it's going to be getting shallower and shallower until it finally reaches the normal depth. You know, eventually, it'll work its way upstream. We'll get away from the effects of that choke, and it'll just be the normal depth. And so there's a little bit of pooling here, just enough pooling to get the water over the obstruction, but it doesn't pool infinitely upstream. It just pools enough so that there's sufficient energy to get over that broad-crested weir. All right. So we are going to try and find out the length of the backwater curve. And what that means is, how far upstream is it until we get to the normal depth? So how far, what is the length from this obstruction, where the depth is 3.8, all the way until things have settled down and it's back to the normal depth, where the normal depth is 1.195 meters. So where it says, what's the length of the backwater curve, we're trying to find out how far until conditions are uniform again. What's the section? This, remember, is UF, meaning uniform flow. And then this part is GVF, gradually varying flow. So what's the length of the backwater curve? Sometimes backwater is a word that's used to describe pooling or non-uniform conditions. The water that's backed up. Okay, our guideline is that we should only have steps at a maximum of 0.5 meters. And so if you think about, we're going from where Y2, the depth is 3.8, and we're going all the way to where Y1 is 1.195 meters. And so we need to break it up into a lot of little steps. And the question is, how many steps should we do if we're having to go from 3.8 up to 1.195? The maximum we can do is 0.5 meters. Well, we just have to divide that total increment, 3.8 meters minus 1.195 meters divided by 0.5 meters per step. And that tells us that we should make 5.21 steps. Now, we can't have a decimal, though. It has to be an integer. And so we're going to use 6 steps. Okay? And so if we use 6 steps, then that means each step is 0.43417 meters. Each step doesn't have to be the same size. I'm going to make each step the same size. I'm going to actually use this increment, but if we wanted to round it off here and there, that would be fine too. What I'm going to do is I'm going to have, this one is going to be 3.8. This is going to be 3.366, 2.932, 2.497, 2.063, 1.629, and 1.195. So in each case, I'm going to be trying to find out how far apart it is. You know, what is the individual length between each of these? And And so in the spreadsheet that we set up, that is what we're going to be finding, is how long is the distance between each one of these steps. And the formula we're going to use is that we can find the length by the difference in the specific energy divided by the difference in the channel slope and the average energy grade line slope. We're going to find the energy grade line slope. Does anybody remember how we find the energy? It's right there. Manning's equation is how we find the energy grade line slope. So we're going to find Manning's equation here, 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 at each one of the points where we know the depth. And then when we find the L, we're going to find the average of the energy grade line slope between here and there and apply it over the increment by finding the average in between the two. Any questions on the method or the logic of what we're trying to achieve?
Will the water flow to the rock crest that we are at the critical depth?
It will. Yep.
Dr. Wright?
Yes.
How did you determine each step size?
Once I found out that I should do at least 5, then I did 3.8 minus 1.195 divided by 6.
Oh, okay.
So this is the total vertical distance that is going to be covered. And I know that there's going to be 6 steps. 1, 2, 3, 4, 5, 6. And so that tells me the vertical step for each, the vertical distance for each step. All right. I'll give you a few minutes to set up the structure of the solution, meaning the column titles, basically to copy what I've got on the screen already, so that when we start putting in formulas, then you won't still be trying to type things in. Don't worry about getting the superscripts and all that. You can do the fancy formatting later if you like. All right. We've got some extra space between the depths because some of the columns are going to be calculated for the midpoint between them. For example, the slope of the energy grade line, S sub F, we need to find an average between them. The delta E is going to be between them. Okay, so this is a rectangular channel, so the area is going to be the depth times the channel width. I'm going to anchor the reference up to the channel width so that I can drag that equation down and eliminate all of these places where it says 0. Velocity is going to be the flow rate, Q, anchor it, divided by the area. Drag that down. All right. E, meaning specific energy, is going to be the depth and the velocity head. So depth plus velocity squared divided by 2g. All right. Give you a moment to catch up.
Did you highlight the last one?
do it this way because I know it freaks some people out. All right. Okay, delta E is going to be the difference between these two. So working upstream, we're going to say the upstream minus the downstream depth. So energy, the delta E is negative because we're working in the upstream direction. Okay, so I've got this formula here. I can do Control C and then paste it. Does that not work as a paste? Yeah. No, that's the wrong spot though. And so the interpretation of that column, in words, we're saying that is the change in specific energy over the increment. Remember, we're solving in steps. A step that on the downstream end is where the depth is 3.8. The upstream end of this step is where the depth is 3.366. And between those two depths, the specific energy change is negative 0.43 meters. Okay, now when we do the hydraulic radius, we're back to doing it for the section itself rather than for the increment. And so the hydraulic radius will simply be the area divided by the wetted perimeter. So the wetted perimeter is 2 times the depth plus the channel width B, anchoring that so that when I drag the formula down, it continues to look up here at this cell. Hydraulic radius is area divided by wetted perimeter. It's always easy when it's a rectangular channel. That'd be awesome if in the final it was like a trapezoidal, right?
No.
You'll get some practice with trapezoidal channels next time. That's actually the essence of the next method, is how to deal with channels that have changing geometry. But we'll keep it easy here for the direct step method.
Why are we taking the upstream depth minus, or the downstream depth minus the upstream depth?
Yeah, like why was it this minus that?
Yeah.
It's because we're working our way upstream. So the difference assumes that we are beginning downstream and working upstream. So here at the downstream location, the origin, the energy was 3.8, and then in the direction that we're working the problem upstream, because this is subcritical, the energy is lower.
Okay.
And so over the increment, there was a decrease in specific energy. Decrease because the direction is that we're working, since it's subcritical, from downstream to upstream. Okay, slope of the energy grade line is using Manning's equation at this location. Okay, so Manning's equation says it's the n value times the flow rate divided by the area divided by the hydraulic radius to the 2/3 power, and all of that is squared.
Dr. Wade?
Yes.
Can you, just on the keyboard, lock the, or anchor
The F4 button.
F4? Okay.
Yeah, if you do that, if you press F4, then it'll immediately throw in those dollar signs so that you don't have to type them.
Why was the lowercase f?
Well, it's because I have my cell centered, and you notice that I can't click on cell F17 because the equation's in the way. If I hadn't centered my cell, then I would have been able to click in it. And so I just typed in its location manually, and so that's why I didn't bother to capitalize F17, but it still knows where I mean. If I had it left aligned, then when I'm typing in the equation, it doesn't get in the way of where I'd like to click. But when it's centered, because I'd previously formatted this to be centered, then it sort of makes it impossible for me to click in that cell because the equation is in it. Okay, so I can drag that down, and we know the slope of the energy grade line at each of the places where we know the depth. So the energy grade line slope, if we want to know the average, that's talking about over the increment. And so the average equals this plus that divided by 2. All right, so now slope of the energy grade line, I'm sorry, the channel slope, anchor that minus the average energy grade line slope. So now this is going to be the denominator when we do the DL function. Now remember that on the final exam you won't be able to open up an existing spreadsheet that you've already created. And so what you'll need to do is you'll basically need to understand the method. And the columns don't have to be in this order. There's nothing magical about the way I've set up this spreadsheet. It's just that over the course of filling it in, we've prepared all of the information we need for delta E and the slope of the energy grade line at the midpoint. So even if all you had was this equation, from this you should be able to derive what you're going to put into your spreadsheet. Like, what do you need the spreadsheet to calculate? Well, specific energy would be nice. And so what's in specific energy? Depth, velocity. All right, so there should be columns that have velocity, column that has specific energy. You know there's going to be a delta E, so that gives you the hint that there should be a column that is calculating the change in energy between each of the locations. There's going to be the slope of the energy grade line over the increment, and so I think there's little hints on what the spreadsheet should look like just in the formula. And so, you know, I always struggle with the idea of, should I show you these beautiful, wonderful spreadsheet templates, or should I make you figure it out on your own? Ultimately, just to show you the method, I show you the template that I've got, but there, you know, I'm sure every one of you would have had a different spreadsheet, and maybe that would have been more meaningful for you, and you'd remember it better if you'd created the spreadsheet yourself. You know, be that as it may, you won't have this for the final exam, so you'll need to understand the method. The last step here to find the DL over the increment, what we're going to say is it is the delta E that we had from over here divided by the difference between the channel slope and the average energy grade line slope. So the last step is pretty anticlimactic when we're just doing one cell divided by another. And what that tells us is that it takes 300 meters for it to go from 3.8 meters of depth to 3.67 meters of depth. So that is the distance just between these two depths. And so we apply that same thing everywhere else. and then we total it all up. The sum of all those incremental depths, 2430 meters. That's how long. And the negative just means it's in the opposite direction of the flowing water, so upstream. We have to go upstream 2430 meters in order to get back to that normal depth. The backwater curve length, meaning the length of the stream, 2.4 kilometers, is how long it's going to take for the water to go from that pooled depth of 3.8 meters decreasing back to its normal depth.
That's like 1.5 miles.
Yeah, it's pretty far. The backwater curve length would have probably been shorter if the slope was greater. We have a fairly shallow slope here of 0.1%, 0.15%. So this is a very shallow stream, which means any disturbance like a broad-crested weir that's pooling water to 3 times the normal depth is going to have a pretty long impact. It's going to be affecting flow for a long ways upstream. So was this enough steps? You know, we could have solved this problem, break it up into 10 steps and see what kind of length do we get if there were 10 different steps rather than 6. Probably would have been pretty close. But, well, Jordan, did you have a question?
Yeah, the total length, what was that again?
It's just the sum of all these individual lengths.
I mean, like, what does it stand for? Is that the backwater?
Okay, yeah, it's the distance. So that 2430 is how long it takes to go from here. Let me draw a line to represent what that is. So 2430 is that length. It's from where the obstruction is, and that where the depth is 3.8 meters, all the way up to where it's normal depth again. So you've seen the direct step method. That's today's lesson, the direct step method. I'm pleased to report I've got another subscriber on YouTube, so the community of hydraulic engineering students is growing. Between the 25 here at Marshall, we've got one in China, one in India, and I'm not sure where this other guy's at. They're human beings. They're actual people who have subscribed to my YouTube channel so that they can watch these lectures.
But it's not other Marshall students.
No, it's not ever other Marshall students. No. No. I've seen the... you want to say hi? Oh, no, they have never said anything. I just get an email when I get a new subscriber. So, all right, looking at the announcements, remember that the next homework you're working on is 13. You've already done numerical integration method. Might as well solve the problem now while you still remember it. Same with direct step. So actually, you can solve 2 of these problems, and then you'll have the rest of the week to solve the other 2. All right. See you on Wednesday.